All right, on a previous video, we found a nice way to use vectors to find the distance from a point to a line in three-dimensional space. Now we can find another way to find the distance from a point to a plane in three-dimensional space. So our problem is to find the distance from the point S216 to the plane 4x plus 6y plus 3z equals 12. So I've kind of drawn a picture here, just a random plane here, but it is important, we need to find a point in our plane, and that's very easy, right? There's an infinite number of points on a plane, so a simple way to locate a point is to let two of the variables be 0. So what I did was I let x and y both be 0, in which case I had 3z equals 12. So I know the point P004 is definitely on our plane. I could have chosen other points, right? I could have let y and z be 0 and found x to be 3. That would be totally fine. The picture, so we also know that a normal vector to the plane has the same coefficients. That's something we discussed earlier. So a normal vector to the plane 4x plus 6y plus 3z equals 12 would be 4, 6, 3. 4i plus 6j plus 3k. Remember that vectors can be placed anywhere. They're just lines. So I'm going to place that normal vector right over our point. And I can make another vector from our point on the plane to point S. And you can tell you can make a right triangle out of this. So D would end up being the distance, this distance here. You may, from previous videos on vectors here, recognize that that's basically the magnitude of the projection of vector PS on vector N. So we're essentially rederiving that formula here. Now, using plain old trig, what trig function would involve D and the hypotenuse, adjacent hypotenuse? That would be cosine. So the cosine of theta equals D over the magnitude of PS. Multiply by PS, so D is equal to the magnitude of PS times the cosine of theta. Notice I left a blank, just like I did on the previous distance formula, because the strategy for finding the formula is very similar. This almost looks like a dot product. What's missing is the magnitude of n. So if I multiply top and bottom by the magnitude of n, which is just like multiplying by 1, I have a nice formula now. The distance between a point and a plane is the absolute value of PS dotted with n, right? This is not a magnitude because a dot product is a scalar. This is just in case my scalar comes out to be negative, because distance has to be positive. And the denominator is the magnitude of n. Using our numbers, it's pretty simple. PS is vector 2, 1, 2. I can dot that with n. Remember, dot product, just multiply the components and add. So 2 times 4 is 8, plus 1 times 6 is 6, plus 2 times 3 is 6. That adds up to 20. The magnitude of n is the square root of 4 squared plus 6 squared plus 3 squared, root 61. So D is 20 divided by the square root of 61 is the distance from point S to our plane. Again, remarkably simple when you know some stuff about vectors.